Hi, it's time for another math easy solution. Today we're going to discuss further into linear differential equations and now go over example 2 of the example series and solve this example, which states find the solution of the initial value problem x squared y prime plus xy equals 1 and where we are given x is greater than 0 and also the initial value y of 1 is equal to 2, or that's a y value when x is equal to 1. So if you recall from my earlier video on linear differential equations where I derived the solution for it, basically what we want is we want to write this as write this in the form of y prime plus a function of x, we'll call it p of x, plus, and then y equals to q of x. So this is the form we went over in my earlier video, and in this one we could do that. We just have to divide by x squared so we can get rid of this in front of the y prime. So what we do is divide by x squared on both sides. So when we do that, what ends up happening is we get this, well, let's just write down what we have, x squared y prime plus xy equals to 1, and we divide both sides by x squared. What we end up getting is over here, this just cancels, so we get a y prime plus x divided by x squared is just 1 over x, and then we have the y, let's make a better plus sign. Then this equals to, on the right side, is 1 over x squared. So what this means is our new p of x is over here, and then our q of x is over here. And now if you recall, the next step is basically the integrating factor, is determining this. And again, make sure to watch my earlier video on linear differential equations, and you'll see why we were doing this. And then basically the integrating factor, recall that it's I of x, and it's equal to, and we just need one solution of it, e to the power of the integral p of x dx. And in our case, p of x is 1 over x, so we have e to the integral 1 over x dx. And now we could begin solving this integral of 1 over x. Recall is just going to be ln absolute value of x, and now we have a constant of integration c, but basically this equals 2 e, and in this one x is greater than 0, so we just write x, and get rid of the absolute value sign, and then c will choose it to equal to 0. And then when we do that, this cancels, this is 0, and I'll write that down right here. So basically we choose c is equal to 0 because we only want one particular solution, and we also have x is greater than 0. So I will put this in a bubble just to illustrate that. And in later videos, what I'm going to do is actually, in my next video actually, I'll prove in detail why we could just choose one of these values, c is equal to 0, so we don't need any general different types of coefficients there. All we need is one particular integrating factor. And in my next video, I'll go over this integrating factor in detail to prove that we only need one, so we could just choose c is equal to 0 in this case. And basically one non-zero integrating factor. So this is a non-zero. So we have x over there. And now the next step is, well, we multiply both sides of the linear differential equation multiply both sides by I of x equals to x in our case. So what we have, now that we have it in this form, let's just write that down first. So y prime plus 1 over x y equals to 1 over x squared. So we multiply both sides by it, by x, so we put an x there on this side as well, x like that. And when we do that, we have this x y prime plus x is cancelled, we just have y equals to here 1 over x squared, and x cancel. So now that we have this, and again, recall the whole point of the integrating factor is so that we have something that looks like a d over dx of the integrating factor times y equals 2 And if you just take the integral, this is going to be this part right here, and you can even prove it by just integrating this using product rule. Deriving this using the product rule, and I'll just move it like that. And basically, the derivative of this is going to be, well, we'll do derivative of y first. So if x and y prime plus derivative of x is 1 plus the number of the value y. So now that we have this is the same thing here. So since this is equal to it, we could bring this down, so this equals to 1 over x. So now we have a separable equation, and again, if you watch my earlier video on linear differential equations, the whole idea is to get a separable equation, and this one we combine the integrating factor, in this case x, with y, and then we can do that. Now we move this dx on this side, so we get is dxy equals to 1 over x dx. And then we integrate both sides. And when we do that, this left side becomes, that's just xy. And then plus, well, constant of integration, we'll call that c1. And then here we have, over here, integral of this is going to be ln absolute value of x plus constant of integration, we'll call that c2. And in this case, now we just move this over, and we also have this as x is greater than 0. So then we can remove that absolute value sign. So what we get is this xy equals to ln x and then plus c, where, and we'll call c is equal to c2 minus c1. And this c is different from the one above, the one where we set equal to 0. This is just a generic constant of integration, and then a subtraction of constants is still a constant, like that. So now we have this. Let's solve for c, because instead of solving for y right away, we could solve for c, because, well, at the initial value y of 1 equals to 2, and let's just show you that. Let's double check. Yeah, so y of 1 is equal to 2. So when we plug those values in, we could solve for c. So we get this 1 is x, so we have 1 times 2 is y, and then equals to ln 1 plus c. Yeah, so that is what we have, and now this part right here, ln 1 is equal to 0. I'll just write this equals to 0, and you can, just a refresher on the properties of power functions, and this is the logarithmic functions. But basically what we have here is, when we have ln 1 equals 0, is the same thing as writing 0 is equal to log base e of 1. And again, recall what this means is that this value is the power of the exponent. I mean, it is the power of the base, which in this case e to the power of 0 equals to 1. So that's what this means. So e is solving, this is 0 is solving this logarithmic function, is solving this power right there. Yeah, so basically ln 1 equals to 0, same thing as writing e to the power of 0 is equal to 1. So anyway, so that's 0, that's just a refresher. You can learn more about this in the video links below. So now we could rearrange, this is 0, so c is equal to 2, like that. So now we could plug that inside here, so we get xy, so let's write thus, xy is equal to ln x plus 2, where c is 2, then divide by x on both sides, get rid of it. So what we get is y of x is equal to ln x plus 2 divided by x, like that. And now if we basically graph it here, I went into Google search graphing calculator, just graph it, you get something that looks like this. There's a ln x plus 2 all divided by x, like that. So when you divide it, you get something like this. I don't know why this is like that. But I just had to play around with the coordinates, for the x and y axis, you just have to move it around and play with it. But anyways, once you rearrange it, you'll see this stuff changes. So anyways, so I copied and pasted here. Yeah, here it is. And also, yeah, I just wanted to clarify this one. This one, the coordinates are just the x-axis needs to be changed. And when you do that, you'll notice, yeah, so just the x-axis wasn't set up properly. But anyways, when you play around with this, you could get something like this, where I've screenshotted here and pasted here. So this is how the function looks like, or the solution to that differential equation, which is pretty interesting. And then just another interesting part is, notice here, as this is the x-axis, this is the y-axis, and this one is, I'm not sure if it's approaching 0 or not. So basically, I'll write as x is approaching infinity, does y approach 0? This is just something I'm curious. Well, not 100% sure because it doesn't look that steep, but we can, well, let's take the limit, see what happens. So limit as x approaches infinity of ln x plus 2 divided by x. Well, what we end up having is the ln x is approaching infinity, and then we have x at the bottom is approaching infinity. So we have an infinity over an infinity. So we can't really solve this, but if you recall L'Hopital's rule, let's recall. And here I've copied and pasted the L'Hopital's rule. It's also it's pronounced L'Hopital, sometimes spelled L'Hospital like that, but it's pronounced L'Hopital. I'm not 100% sure which one is the more common one, but it's the one I've been growing up using. So write it better as 0. So this is what it is, and basically, you can learn more about this in video link below. I did a proof video on this. But when you have limit as, in our case, x approaches infinity of f of x divided by g of x, this equals to the limit of the derivatives f prime of x divided by g prime of x, for the cases when you have something like a plus or minus infinity divided by a plus or minus infinity. And this is assuming both of these functions are differentiable, meaning the derivatives exist. So, and again, you can learn more about this in the video link below in my earlier video. So when we have this, we could apply that in our case and see that the limit as x approaches infinity of ln x plus 2 divided by x, this equals to, and now we take the derivative of the top and bottom of it. So x approaches infinity of d over dx ln x plus 2 divided by d over dx of x, like that. So the derivative on top, that's going to be, well, we'll just write this down. This is going to be limit as x approaches infinity of 1 over x. Then the bottom one, dx over dx, that's just, that's just 1. So we have this limit as x approaches infinity of 1 divided by x. So what we have is a 1 divided by infinity, or in other words, it's approaching 0. 1 divided by a large number, it's getting smaller and smaller. So what this means is this is actually equal to 0. So this means this is eventually going to 0. So this is correct. It does actually go to 0. And one way of understanding why it actually goes to 0 is because you have to basically look at which side is increasing faster, the top or the bottom side of this, the numerator or the denominator. So for example, if you look at a little graph like this, and the logarithmic function looks something like this. It curves like that. This is y equals to ln of x. This is the x. That's the y curve. But so that's y equals ln x. But the bottom part is just this one. And again, we just ignore the plus 2, because when you go to infinity, you're just adding 2. It's not changing too much. But then the y. But then when you have the y equals x line, it looks something like this. So this one is the y equals to x. So as you can see, this one's increasing to infinity much faster rate than this one. So that means at infinity, or approaching infinity, this one you're dividing by a larger number that is approaching 0. But since they're both going to infinity, it's not approaching it as quickly, but it's still nonetheless approaching infinity. Put this in a bubble. Okay, yeah, so that's pretty much all for today. Just wanted to go over this in more detail at the bottom here. It's pretty interesting stuff. Anyways, that's all for today. If you'll learn, like always, you can download these exact notes in the link below. And thanks for watching, and stay tuned for another Math Easy solution.